For decades, we've pictured Mars as a dead desert world, a planet of dust and rock, where water is just a ghost, locked away in polar ice caps or maybe hidden deep underground. The Mars we think we know is silent and frozen, a beautiful but barren testament to a cosmic history that went catastrophically wrong. It's the poster child for a planet that lost its shot at life. But what if that whole picture is wrong? Scientists have just made a shocking discovery that is rewriting the history of the red planet. They haven't found a small, lonely stream or some ancient trickle of water. They've uncovered a colossal, interconnected network of ancient rivers, stretching for 15,000 kilometers. To put that in perspective, that's a distance that could stretch across the United States from New York to Los Angeles 5 times over. This isn't just a sign of a little water, it's evidence of a wet and wild past, a world with a dynamic climate and vast flowing river systems. And it forces us to ask the ultimate question: if the rivers were there, what could have been hiding within them? The story of this discovery doesn't begin with a rover kicking up some new dust. It starts with scientists painstakingly poring over high-resolution images taken from orbit, looking at a part of Mars that had long been overlooked. The region is called Noach's Terra, or the Land of Noah, a heavily cratered ancient slice of Mars's southern highlands. For a long time, this area was a real puzzle. Climate models predicted that this part of ancient Mars should have been wet, but the classic signs of water, those big branching valley networks, were missing. It led many to believe that maybe Noach's Terra had just stayed dry, a holdout against the watery past suspected everywhere else. This new research proves just how spectacularly wrong that assumption was. A team of scientists, using combined data from multiple orbiters, specifically NASA's Mars Reconnaissance Orbiter and Mars Global Surveyor, didn't look for valleys. Instead, they hunted for a more subtle clue: winding, snake-like ridges that actually rise above the surrounding terrain. What they found was staggering. Across this ancient landscape, they mapped out nearly 10,000 miles, or 15,000 kilometers, of these ridges, forming complex, interweaving systems. Some were short, isolated segments, but others stretched for hundreds of kilometers at a time. This is a profound revelation. It represents a fundamental shift in how we see Mars's history. For years, the prevailing theory was that early Mars was a predominantly cold, dry planet. Any water that flowed was thought to be from catastrophic, short-lived events, like a volcano melting massive sheets of underground ice, causing brief but violent floods. These events would carve huge outflow channels, but they wouldn't last. The water would quickly freeze or evaporate, and the planet would snap back to its frozen state. But these 15,000 kilometers of rivers tell a completely different story. Their sheer scale and their interconnected branching patterns aren't the signature of a flash flood. They're the signature of a persistent, stable water system. They are evidence of a planet where water flowed consistently over geologically significant periods. This discovery challenges the cold and dry model to its core, replacing it with a vision of an early Mars that was far warmer, far wetter, and way more Earth-like than we ever dared to imagine. The implications are almost overwhelming. We're no longer talking about a planet that might have had a few temporary lakes. We're talking about a world that once hosted sprawling river networks, a planet with an active and sustained water cycle. But that raises an immediate and fascinating question. If these rivers flowed billions of years ago, how could any evidence of them possibly survive to today? The answer lies in a bizarre and beautiful geological process that turned these ancient rivers to stone and preserved them like fossils. The key to this whole discovery lies in features known as fluvial sinuous ridges, or more simply, inverted channels, and they are exactly what they sound like: ancient riverbeds that now stand as raised ridges, proud of the Martian landscape. The process that creates them is a perfect act of geological preservation. Imagine a powerful river flowing on Mars, 3.5 billion years ago. It carves a channel, and as it flows, it carries heavy stuff: sand, gravel, and rocks. This sediment settles on the riverbed, and over eons it gets packed down and cemented together, becoming much harder and more resistant than the soft soils of the surrounding floodplain. Then, Mars's climate changes. The atmosphere thins out, the planet gets cold, and the river dries up, leaving its hardened, sediment-filled channel behind. For billions of years, Mars becomes a world of wind. The thin atmosphere, carrying fine dust and sand, acts like a relentless sandblaster. It slowly but surely erodes the surface. The softer material of the ancient floodplain is gradually stripped away, layer by layer. but the cemented, hardened riverbed. It resists that erosion. And so, as the landscape around it lowers, the riverbed is left behind, standing high above the plains. The channel becomes a ridge. The river is literally turned upside down, creating a fossilized map of its path across the ancient world. These are the structures scientists have mapped. These ridges are geological ghosts. Some stand tens of meters above the surrounding terrain, winding for hundreds of kilometers. Looking at the images, you can trace their meanders, see where their banks once burst, and even spot where tributaries once joined. They are a perfect three-dimensional map of a lost water world. But the story gets even more exciting. Recently, another team of researchers, using data from the Curiosity rover, developed a new way to spot river deposits that don't form these obvious ridges. They trained sophisticated computer models on a combination of rover images, satellite data, and, incredibly, 3D scans of ancient river layers from deep beneath the seafloor of the Gulf of Mexico right here on Earth. They taught the model to recognize the subtle, eroded signatures of river deposits on Mars. When they ran the simulation, it revealed that common formations inside Martian craters, previously thought to be something else entirely, are actually the eroded remnants of ancient riverbeds. These are known as bench and nose landforms, and until now, nobody knew what they were. This breakthrough suggests there could be countless undiscovered river deposits all over Mars, hiding in plain sight. It means the 15,000 kilometers already found might just be the tip of the iceberg. And we have even more direct evidence. In other parts of Mars, like the massive Hellas impact crater, orbital images have revealed stunning cross-sections of cliff faces. These images show 200-meter-thick stacks of layered sedimentary rocks. This is not the work of a flash flood. This is the unmistakable signature of powerful, long-lived rivers, actively depositing sediment, building up floodplains, and shifting their courses over immense timescales, just like the Mississippi or the Nile here on Earth. The layers in these rocks are like pages in a history book, telling a story that likely unfolded over tens or even hundreds of thousands of years. This brings us to the next massive piece of the puzzle. If Mars had this much water for this long, where did it all come from? For years, the go-to explanation for water on Mars was glacial melt. The idea was that massive ice sheets would occasionally melt due to volcanic activity or large asteroid impacts. This would release huge volumes of water in catastrophic but temporary floods. This model fit with the idea of a planet that was, on the whole, cold and dry. It allowed for water, but only in brief, violent bursts. However, the discovery of 15,000 kilometers of intricate meandering river systems blows that model out of the water. A flash flood carves a straight, chaotic channel. It doesn't create the graceful looping meanders and widespread tributary networks seen in Noach's Terra. The sheer geographical spread of these rivers makes a single source like a melting ice sheet pretty much impossible. The water had to be coming from a source that could supply it across a vast region for a very long time. The research points to one inescapable conclusion: precipitation. We're talking about rain or possibly snow. This finding fundamentally transforms our picture of early Mars. It means that during the Noachian period around 3.7 billion years ago, Mars likely had a much thicker atmosphere than it does today. It was an atmosphere capable of trapping enough heat to keep the planet warm and supporting an active water cycle. Water would have evaporated, formed clouds, and then fallen as rain or snow, feeding these sprawling river systems. This wasn't just a planet with water on it, it was a planet with weather. And this wasn't a fleeting phase. Geological analysis at sites explored by NASA's rovers provides a stunning timeline for this wet era. Studies suggest that rivers and lakes were long-lived, potentially existing for millions of years, in places like Gale Crater, the home of the Curiosity rover. At Jezero Crater, where the Perseverance rover is right now, evidence points to a crater lake that was up to 35 kilometers wide and 30 meters deep. This kind of stability is crucial. A brief flood is a geological curiosity. A million years of flowing water is a world-building engine. It's enough time to create complex geological features, and as we'll see, it's more than enough time for something truly extraordinary to happen. The story doesn't even end with rivers. Further evidence suggests these colossal river systems were flowing somewhere. Geological studies of ancient deltas, where rivers meet a large body of water, have been identified all over the planet. The presence of these features on Mars is powerful evidence that many of these rivers may have been emptying into vast, stable lakes or even a possible ocean, which many scientists believe may have covered the northern lowlands of the planet. So let's assemble this new picture of ancient Mars. We have a planet with a thicker, warmer atmosphere. We have a global water cycle with clouds and precipitation. We have a 15,000-kilometer network of rivers flowing consistently for geologically significant periods of time. And we have these rivers emptying into large lakes and possibly a northern ocean. The red planet wasn't always red. Billions of years ago, it may very well have been a blue planet, a true sister world to our own. This vision of a warm, wet, and Earth-like Mars leads us directly to the biggest question of all. If the conditions were so similar to Earth's, could Mars have also hosted life? This is the ultimate "so what" question. Why does finding ancient rivers, billions of years after they've dried up, matter so much? It matters because it fundamentally supercharges the case for ancient life on Mars. On Earth, river corridors are cradles of life. They are dynamic ecosystems that transport nutrients, support complex chemical cycles, and create stable, habitable environments. The evidence that Martian rivers behaved in a similar way, building deltas and floodplains over long periods, suggests they could have provided all the same ingredients necessary for life to emerge. The immense duration of water activity is perhaps the most critical factor. The potential for long-lived, stable water in places like Gale and Jezero Crater is a game-changer. Life, as we understand it, needs time to get started. A fleeting flood isn't enough. But hundreds of thousands or millions of years in a stable, watery environment provides a huge window of opportunity for the complex chemistry of life to begin. What's more, the very geological process that preserved these rivers is also the perfect mechanism for preserving signs of life. The sedimentary rocks laid down by these ancient rivers are time capsules. As sediment settled, it could have trapped and buried any organic material or chemical traces left behind by microbes. The same process that turned the riverbed to stone would have also protected these potential biosignatures from Mars's harsh surface radiation for billions of years. These fluvial sinuous ridges aren't just a map of where the water was. They are a treasure map pointing to the exact locations where we should be looking for Martian fossils. And this is precisely what NASA is doing. This new understanding isn't just a fascinating theory, it is the strategic foundation for our current exploration of Mars. It's no coincidence that the Perseverance rover was sent to Jezero Crater. Scientists chose that landing site specifically because it's an ancient river delta, a place where a mighty river once flowed into a large crater lake. Perseverance is, at this very moment, driving on the deposits of that ancient river, analyzing the chemistry of the rocks and collecting samples that will one day be returned to Earth. And it has found a diverse range of organic molecules preserved within these ancient waterlogged sediments, the building blocks of life as we know it. This discovery of 15,000 kilometers of rivers elevates the search for life from a hopeful quest to a strategic hunt. It tells us that habitable conditions weren't just confined to a few lucky craters, they were likely widespread across the planet. If rivers were this common, then the potential for life wasn't an isolated possibility. It was a planetary-scale opportunity. The vision of ancient Mars is no longer a mostly barren world with a few small oases. Instead, it's a world where huge portions of the planet may have once had the right conditions for life to begin. It radically changes the odds in humanity's most profound search. Discoveries like this are rewriting our understanding of the cosmos, page by page. We're living in a golden age of planetary exploration, where every new image and every piece of data has the potential to change everything. If you want to stay on the cutting edge of space discovery and be the first to know about the next mind-blowing find, make sure to subscribe and hit that notification bell. The universe is full of secrets, and together, we are going to uncover them. We started with the familiar image of Mars, a cold, red, desert world, but science has peeled back the layers of dust and time to reveal the ghost of a very different planet. We've journeyed from a simple picture of a desolate landscape to the staggering reality of a 15,000-kilometer network of fossilized rivers. We've discovered a world that once had rain, rivers that flowed for ages, and that may have even hosted a vast northern ocean. This isn't just a geological curiosity, it's a blueprint. It gives us a map, showing us exactly where to look for the signs of ancient life. The search is no longer a shot in the dark. We are following the water, and the trail is leading us to the most promising locations in the solar system. Every rock sample Perseverance collects, every new ridge mapped from orbit, is another step toward answering one of the greatest questions we can ask. Are we alone? The red dust of Mars may be covering the remnants of a second Genesis, a separate story of life that rose and fell billions of years ago. We don't have the answer yet, but for the first time in history, we know exactly where to dig. The story of Mars isn't over. In a very real sense, it's just beginning.